Welcome to this scientific lecture on the ideal final result, or IFR, a powerful systematic innovation method that transforms how we design solutions. The IFR technique asks us to imagine the perfect system, one that performs its function by itself, with zero cost, zero complexity, and zero harm, then work backwards to practical designs. Let us begin by understanding the fundamental concept behind the ideal final result. The ideal final result is a mental model where the desired function happens automatically without any additional system. Mathematically, the IFR represents infinite value, the desired function divided by cost, plus complexity plus harm, approaching infinity as the denominator approaches zero. In the ideal system, natural physical phenomena do the work instead of engineered hardware. Physics becomes our mechanism. Compare a current system loaded with motors, sensors, controllers, and power supplies versus an ideal system where the function simply happens by itself through clever use of natural phenomena. The IFR rests on three fundamental pillars that define what makes a system ideal. First pillar, zero cost. The ideal system requires no money to build, maintain, or operate. Second pillar, zero complexity. The ideal system has no parts, no assembly, no intricate mechanisms. Third pillar, zero harm. The ideal system produces no waste, no pollution, no negative side effects. This progression shows complexity reduction from current systems with many components to better systems with fewer components to the ideal with minimal or no components. This raises a crucial question. Is the ideal solution really impossible, or is it just unfamiliar? Often what seems impossible is merely unprecedented. Now, let us develop a rigorous mathematical framework for analyzing system ideality. Ideality equals the sum of all benefits divided by the sum of all costs, plus the sum of all harms. As we approach the ideal final result, ideality approaches infinity, because the denominator approaches zero while benefits remain. The limit as costs and harms approach zero, ideality approaches infinity. This graph shows how ideality grows dramatically as we systematically reduce costs and complexity, demonstrating the exponential improvement possible through IFR thinking. Let us perform a quantitative cost-benefit analysis, comparing traditional versus ideal approaches. Net value equals benefits minus the sum of manufacturing costs, operating costs, and disposal costs. Consider a traditional system example, an active cooling fan for electronics. Compare an active fan costing $50, consuming 10 watts, lasting 3 years, versus a passive heatsink costing $5, consuming 0 watts, lasting 30 years. The 10-year cost of the fan system is $50 initial plus 10 watts times 12 cents per kilowatt hour times 24 hours times 365 days times 10 years, plus replacement costs, totaling approximately $1,200. The 10-year cost of the passive heatsink is just $5, with zero operating costs. The savings ratio is 1,200 divided by 5 equals 240 times more cost-effective for the passive solution. Now let us examine a concrete example, self-cleaning surfaces inspired by nature. The traditional approach uses active cleaning, detergents, scrubbing, water, energy, and human labor. Nature provides a superior solution, the lotus leaf effect, which uses microscopic surface structures to make water bead up and roll off, carrying dirt away. The lotus leaf surface has microscopic pillar structures that create air pockets, making water droplets roll off easily, carrying contaminants away without any energy input. Cleaning efficiency equals dirt removed divided by energy input. Traditional cleaning achieves 95% dirt removal but requires 500 joules of energy per cleaning cycle. The lotus effect achieves 90% dirt removal with essentially zero energy input, giving theoretically infinite efficiency. Our second detailed example examines passive thermal regulation systems. The engineering challenge is to maintain stable temperature without thermostats, heaters, or air conditioning. A passive system uses thermal mass materials with high heat capacity, combined with strategic ventilation channels that open and close based on temperature differentials. Phase change materials provide even better performance by absorbing or releasing large amounts of heat at constant temperature during melting or freezing. The heat absorbed or released equals mass times latent heat of fusion. Example, 10 kilograms of phase change wax with latent heat of 200 kilojoules per kilogram can store 2,000 kilojoules of thermal energy, equivalent to running a small heater for over half an hour with no electrical input. This graph compares temperature variation over 24 hours, without phase change material showing large swings of plus or minus 6 degrees, versus with phase change material showing only plus or minus 1.5 degrees variation. Our third example explores self-powered sensors that harvest energy from their environment. Traditional sensors require batteries that must be replaced or wired connections to external power, adding cost and maintenance. Energy harvesting from ambient sources eliminates the power supply entirely, achieving closer to ideal. A piezoelectric generator converts mechanical vibrations directly into electrical energy, powering a wireless sensor indefinitely without batteries. Power generated equals a piezoelectric constant times area times frequency times displacement squared. Consider a numerical example, a sensor monitoring bridge vibrations. With area 10 square centimeters, vibration frequency 30 Hz, and displacement 0.5 millimeters. This generates approximately 50 microwatts of continuous power. Modern ultra-low power sensors need only 10 to 20 microwatts in sleep mode, making this entirely self-sufficient. Battery life transitions from finite to effectively infinite, with energy harvesting approaching the ideal of zero external power. Let us conduct a rigorous numerical thought experiment, comparing real versus ideal performance across multiple metrics. Consider a water pump system for irrigation as our case study. Compare three approaches: electric pump at $800 and 2 kilowatts, solar pump at $400 with no grid power, and gravity-fed system at $100 with zero power, approaching ideal. Define efficiency as water delivered divided by energy input. Electric pump efficiency, 100 liters per minute divided by 2,000 watts equals 0.05 liters per minute per watt. Gravity-fed efficiency, 100 liters per minute divided by 0 watts approaches infinity, the theoretical ideal. Now let us analyze weight and complexity as quantitative metrics of ideality. Specific function equals function value divided by system mass, similar to specific impulse in rocketry. Example, temperature regulation for a 100 cubic meter space. HVAC system weighs 150 kilograms, enhanced insulation 50 kilograms, but optimal architectural design achieving the same temperature stability weighs 0 additional kilograms. HVAC specific function, 100 cubic meters divided by 150 kilograms equals 0.67 cubic meters per kilogram. Design-based specific function, 100 cubic meters divided by 0 kilograms approaches infinity, again approaching ideal. Now we address the practical methodology. How do we systematically work backwards from the ideal to achievable solutions? Step 1. Define the pure function you want, completely divorced from any implementation details or current technology. Step 2. State the ideal final result. The function happens by itself, with no system. Step 3. Identify exactly what physical or practical barriers prevent achieving the IFR. Step 4. Find the minimal additions or modifications that overcome those barriers while staying as close to ideal as possible. This decision tree shows working backwards from IFR at the top through progressively more practical but less ideal solutions until reaching implementable designs. Let us apply this methodology to a detailed case study. Self-sealing materials. The desired function, prevent fluid leakage from a punctured container. The IFR, the hole seals itself instantly with no repair mechanism needed. What prevents achieving this ideal? Conventional materials have no built-in sealing response to damage. Solution closer to ideal. Embed liquid sealant in microcapsules throughout the material structure, so punctures break capsules and sealant flows into gaps automatically. Response time, 0.1 seconds for self-sealing versus 600 seconds for manual repair, a 6,000-fold improvement. Added mass, only 5% for embedded microcapsules versus 200% for carrying a complete repair kit. A major challenge in applying IFR is overcoming psychological barriers that limit our thinking. Psychological inertia causes us to assume we need a physical thing to perform any function. The key question to ask: can the environment itself provide this function naturally? Shift from component addition thinking, where we add parts to solve problems, to physics utilization thinking, where we harness natural phenomena. Return to our central question: is the ideal solution really impossible, or is it just unfamiliar territory we have not explored? History consistently shows that yesterday's impossible becomes today's standard practice. Now let us discuss the practical strategy for implementing IFR in real engineering projects. Define an ideality score, 1 minus the ratio of actual cost to maximum acceptable cost, minus mass ratio, minus harm ratio. Track the ideality score through design iterations to ensure progress towards the ideal. Target the highest possible ideality score by systematically eliminating or minimizing costs, mass, and harm.